Alright, so we're going to explore a little bit further how we describe the motion of an oscillation. And we're going to get into some of the equations that we used in lab on Tuesday. So we've already introduced the idea of period. So this is the time for one oscillation. And this is going to be in units of seconds. But we're going to introduce a new variable here called frequency. And frequency is the number of oscillations per unit time. So this is going to have units of 1 over a second, which is equal to a hertz. And as their units imply, they are inversely related to each other. So the period is the inverse of frequency, or frequency is the inverse of the period. And we're going to see some similarities between the circular motion that we've learned about earlier in the semester and explored in the prior chapter to this oscillation up and down of the spring. So if you look at an object orbiting, if I were to be able to take this circular motion here and instead of looking at it like a circle, but to be able to follow it straight down, and we were to look at it edge on rather than face on, it would look like, oops, I need another circle there. It would look like the object was oscillating back and forth, back and forth, back and forth. So a circular orbit, what looks like a circular orbit face on, actually looks like an oscillation back and forth when you look at it edge on. Very similar to our spring oscillating back and forth. So I can take my velocity equation and our tangential velocity equation and relate them to each other. So let's do this at the particular moment right here, where we're going to find that we're at the amplitude. So we can rewrite this as this relationship here. And that's usually the best way to be able to see this. So I'm able to take the square root of a. The a here in this particular case is our r. And of course velocity matches velocity. So this connects together here, this idea that our angular velocity of our oscillation is equal to the square root of k over m. Except instead of calling it angular velocity, now we're going to call it angular frequency. Alright, angular frequency is also equal to 2 pi times our regular frequency. Angular frequency is still going to have units though of radians per second, so that part hasn't changed. We're just giving it a slightly different name in terms of oscillations rather than something rotating. So if we set these two equations here equal to each other, we get frequency is equal to 1 over 2 pi times the square root of k over m. And if we take the inverse of that, we can find that, just like this equation up here, period is equal to 2 pi times the square root of m over k, which is the relationship that we used in lab on Tuesday.